successful operation.
Okay, so thank you very much. I'm very happy to be allowed to speak on such a nice conference. And this is, I would like to continue speaking about big Ramsey degrees, which Natasha has beautifully introduced on the first lecture of this event. So I'm very lucky because I don't need to include the introduction, which usually takes me the full slot. And actually, in my talk, the big Ramsey degrees are more of the motivation than the main topic. So I will make a kind of a big picture overview where we are standing. So what we are trying to do, we are trying to study big Ramsey degrees of different homogeneous structures. And we are trying to follow what happened in the small Ramsey degrees area, which started by Neschetřes-Redl theorem. And today we know a lot of Ramsey classes, which are very useful for some applications, and they are motivated by the KPT theorem these days. The big Ramsey degrees is kind of natural infinite generalization of this idea. And there are much fewer results than in the small Ramsey degrees. And you can sort of characterize them by the proof techniques. So some of the big Ramsey degree results follows directly from the Ramsey theorem. Now, the Ramsey theorem is essentially the big Ramsey degree result for omega, because omega is what it operates on, and you can do some kind of easy tricks to extend it to the structures with unary languages, only, no binary relations, and that also corresponds to ultrametric spaces and other cases. So the first sort of interesting big Ramsey results are those which are based on the Millikan's tree theorem, which is the original technique due to Levre. And the original problem was the order of the rationals, and it was extended to a random graph. And you can push it to the kind of simple structures, as they are called in the Natasha's and Norbert's Laflamme's paper. Basically, those are structures which are described by very simple forbidden configuration on two vertices, not on these three vertices. And you cannot do that much with that. So the next important step was the Natasha's work on the triangle-free graphs, for which she introduced a completely new technique, which is based on the coding trees, which are the trees which are no longer symmetric, like in the Millikan's tree theorem, but they have a distinguished coding nodes. And these distinguished coding nodes makes the proof kind of mysterious. And you need to use a technique of forcing, so which you like, but because I'm coming from the background of combinatorics, I consider it a dark magic, and I'm trying to understand it the other ways as well, which is quite a challenge. Like at the moment, there is no other proof of the Natasha's theorem. You can prove the big Ramsey degrees of triangle-free graphs, but you cannot prove it with the coding trees. You have to do it differently. So this technique was extended by Ady Cukr to from free amalgamation classes and other examples. And then there's this Millikan tree theorem, which can be used in the product form, and we are using it to handle the higher arities languages. But again, without forbidden configurations. The forbidden configurations gets quite mysterious. And the last technique, which is based on the Carlson-Simpson theorem, gets you relatively easy proof of the triangle-free graphs, and it can do some other things like partial orders and metric spaces, and those doesn't follow from the other techniques. So they have kind of unsatisfactory situation because it's not clear which technique you want to use for a favorite structure. So what we are trying to do, we are trying to find the theorems which would work for all of these cases. And the basic idea is that every big Ramsey degrees results is based on a tree theorem. These trees are somehow appearing as they are demanded by the nature of the problem, because you can always enumerate the structure and you can color by the shape of the subtrees. So basically, every big Ramsey degree result should be some kind of a tree theorem. So this is example of a tree which you can use to prove big Ramsey degrees for K4 free graphs. And it's different from what Natasha does, because basically what we do is that we are gluing together all the possible enumeration of the homogeneous structure. And the basic idea is that you recover more symmetry this way, because there is no very symmetric enumeration of free amalgamation classes. But you can, if you consider all the possible enumerations, you get the symmetry back. But what you get as a new complication is that the tree is growing with increasing branching. And also the tree is relatively complicated. So basically it works in the way that it is describing one vertex extensions of the enumerated graph. So in my picture, there are always these dots are the enumerated vertices, and the cross on the top is a one vertex extension. And the successor relation here means that, for example, this thing can be extended into this thing by adding a next enumerated vertex. So that's how the tree grows. And the tree includes every coding tree. So this is the example of the coding tree of the K4 free graph. And you can find it as a subtree of this huge tree. And you can define the structure on that tree, which is K4 free, but I'm not going to verify it because it's a messy picture. But that's the basic idea how the proof goes. So the main problem is that now you have a whole new kind of a tree. And for the tree, you need a tree theorem. So we was looking into a way to abstract this. So the proof can be somehow split into two parts. You would have an abstract tree theorem, and you would have the structural construction on the top of it, which is sort of what happens in the finite world, because you have the partite construction. And that one is based on hyperlocality theorem and the Ramsey theorem, and doesn't need a specific theorem for every new problem. So tree for me is the usual thing. It's a partially ordered object where every downset is linear and has a finite size. And we have something which we call the S tree, or the tree with the successor operation. And it has the nodes of the tree, which is a T. It has the partial order, and it has some language sigma, and then it has a successor operation. And it works in the way that the successor operation has to satisfy a couple axioms. And the first axiom is that if you build a successor of a given vertex A, and it has another two parameters, which we call the parameter and the character, you always get the immediate successor of the given node in the tree. So it's indeed the operation is making successors as a partial operation. So that's the first property. The other property is that the successor operation should be injective. That means that you don't have two ways to build one vertex, which would make things complicated later. And the last property is that every node in the tree, which is not a root, can be constructed by means of the successor operation. So basically, the successor is fully describing the tree, except for the roots. So those are the basic properties. And now, in order to state the theorem, and I hope I will have the time to do it this time, because the first time I was giving the talk on the ultramass, I didn't get to the statement. So the idea is that, so to state the theorem, you need some basic operations with the nodes of the tree. So this is how it works. This is an example how it works for binary trees. So for binary trees, you can keep these parameters to be always empty sequences. And basically, if you want to describe a given node of the tree, you are basically saying that this is the successor of the root with character 0, which is describing this, and the successor of it with character 1, which is describing this thing, and so on. So basically, you can build words by repeated successor operations. And now what we need to do, we need to look on the nodes of the tree as both nodes and also as kind of the expressions or terms of the successor operation. So we have something which we call the S term, which is defined recursively as basically describing how you build from the given level. So you specify the level n, how to build a given vertex by means of repeated successor operations. So that's what the recursive definition says. So we call it a level n decomposition of the node. And once you have these decompositions, this is the example how it works. So if you want to decompose 0, 0, 1 on a level 1, so the predecessor of 0, 0, 1 on the level 1 is 0. And then you say, okay, start from the node 0, add the character 0, and add the character 1, and you get 0, 0, 1. So this is the basic idea. Now, once you have these terms, you can actually manipulate them. So you can, for example, replace some occurrences of the nodes by different nodes, which is the meaning of this operation. So you can specify the function which is translating some nodes to different, and by means of that, you can change the term. And by this, you can say what is removing of the level. So this is very intuitive with the words. You simply take a given character and erase it from the word. And you can do the same definition on successor operation. So basically, what you do is that you specify the level n. Then you take your node A, and you decompose it on the level n. And then on level n, you will be using some nodes, and you simply replace them by the immediate predecessor of them. And then you reconstruct the same construction, and you arrive to a different node. So that's a complicated way how to say that you have erased one successor operation on the given level. And here is an example. So if you want to erase a character on the level 2, you arrive from 101 to 11. That's the basic idea. And the another operation which we need, it's the last one, so you don't need to suffer too much, is the duplication. And the duplication basically says that you take a node which is called B, and then you decompose it to some level n, and on that level n, you repeat the precisely same successor operation as happened on the level m before. So basically, that means in the words, it means that I take the character from position 3 and I cut and paste it to the position 5. And this operation is also possible to do in this formalism. So that's the basic two definitions. And now you need to define what the subtrees are. And the basic idea is that the subtrees should have the same shape as the original trees. This is different from the Millikan's theorem, because Millikan theorems in this increasing branching gives you wider and wider trees, which is a very interesting property of the theorem, but it is actually not good for this setup. It's not what we want. So basically, the idea is that we have the shape preserving functions which are embedding from the tree to itself. And they have to be level preserving, because if you have the strong subtrees, it's a level preserving mapping. And it also has to preserve this S operation. So that means that whenever I'm in the original tree and I have the A and I have two successors, B and C, which are built by means of some S operations, if I look to the image and I build the successors the same way in the image, then I need to be able to find a successor of those on the next level of the image of my tree. So this is really very similar to the notion of the strong subtree, because in the strong subtree, every immediate successor has a successor on the next level. Here the selected successors, which are nice, and they have a meaning for the successor operation. They have successor on the given level. So, like for binary tree, this is exactly the notion of the strong subtree. And then, yeah, there are no restrictions. Yeah. You can go anyone, and yeah. You can actually restrict this theorem, and you can add restrictions if you want. But yeah, in the version which I put on the slides, yeah, we made it easy. So here. This is just the set of the mappings from S to S prime, which are shape preserving, and with that you can formulate the theorem. So I at least got to the formulation of it this time. So basically, you have a S tree, and you assume some things about the S operation, which I will say later, and then it continues exactly the same way as the Millikan's tree theorem. So for every finite coloring of the shape preserving embeddings from the initial part of the tree to itself, there exists a shape-preserving embedding from the tree to itself, such that the coloring is monochromatic on it. That's what Millikan's tree theorem promises. And basically, you need to verify these three properties. So you need to verify that removing levels is not a complication. So if you remove the level, the node still exists. Because it might not exist because the successor is partial operation, you need to be able to duplicate levels. And then there is the last property, which is sort of related to the Stevos amalgamation axiom. You need to be able to break every embedding into the initial part and the tail. That's kind of the problematic one. But without that, we don't know how to make the fusion work. So those three axioms are usually relatively easy to verify, and if you verify them, you get Ramsey theorem. So I think I have something like I don't know, 6 minutes left. So little bit 5 minutes. Okay. Yeah, I didn't want to speak much about the proof because there is no time for it. But the proof is actually not very complicated, which is the point of the whole exercise. So the one-dimensional pigeonhole can be done by Hell's-Jewett theorem. That's where you use this duplication axiom, because Hell's-Jewett is basically duplicating things. Then you make the infinite-dimensional pigeonhole by adaptation of the comaterial forcing method, and then you just repeat the proof of the Millikan's theorem from the hyperlocally theorem by fusion, and you get the full result. To just give you a very brief idea how you can derive the big Ramsey degrees from this. So this is the theorem by Andy Zucker, which is a generalization of the Natasha coding node technique, and it's until now it had only forcing-based proof. So basically, it says that if you take the free amalgamation class in the finite binary language with finitely many constraints, you have finite big Ramsey degrees. And I will show it in the example when I forbid K4, because K4 is the easiest example, which is not handled by the Carlson-Simpson method. So basically, the idea is that you get this tree, which I was briefly introducing on the beginning. So the nodes of the tree are K4 free graphs. And they have enumerated K4 vertex extensions of the K4 free graphs, and here is a K4, so you need to take it away. No, it's not. I did it correctly. And basically, this is the definition of the node. So the node is a K4 free graph. It has the enumeration and extending vertex, which is T. And it has something which we call the free level function. So every vertex has associated level, which is strictly below. And all the edges has to go below that level. This is a technical property which is needed to make the theorem work. And we don't fully understand why it should be that way. And the important thing is that you can rebuild a bigger graphs using the one vertex extensions, which are smaller. So this is the one vertex extension I'm building. And I'm trying to add the vertex 4. So what I do is that I take away the vertex 4, and I get the immediate predecessor in the tree, which is B. And then I describe the vertex 4 by means of another node of the tree, which is this parameter for the successor operation. So the parameters are sequences of the nodes of the tree, which are strictly below the level of the tree which I'm extending. And that's where the free level is necessary, because we cannot take it from the same level as B, and it has to be strictly below. And then if you put them together, all of the thing which remains to be defined is if there is an edge or non-edge on the top. And that's the finite character information. So basically, every vertex decomposes to the earlier vertices. That defines the successor operation. And this is how the tree looks like. And then you verify all the axioms. And the first three axioms, which is kind of that S is well defined and injective and everything can be constructed, follows from what I just said. And then the rest of the axioms are sort of trivial in this setting, because removing a vertex from K4 free graph doesn't make it K4 free. Duplicating a vertex doesn't make it K4 free because it's a strong amalgamation class. And the decomposition is yeah, it's something which you need to verify, but it follows quite easily. So basically, that's a complete proof of the superstar theorem by application of this technique, or at least a basic sketch of it. Okay, so I think I have used my 5 minutes, right? So I will just stop on the position where we are right now. So we can generalize this theorem, and we can handle some strong amalgamation classes like metric spaces, because those was following from the Carlson-Simpson method, and this is sort of generalization of the Carlson-Simpson theorem. And we can do this to pretty much all the Charlin's graphs. We also can verify the axioms of the Ramsey spaces, except for this A32 axiom, which is the problematic one. But because Stevo has revisited his proofs, he can get the Galvin-Chikri theorem. We can prove the Galvin-Chikri for S3s. And what's where we are stuck right now? We are not able to forbid this particular clique in the ternary language. So there's a clique with the 4 vertices, and there's a one ternary edge, which is the pink one, and there are some binary edges, which are the remaining ones. And this is the moment where the proof breaks, because the axiom 6 is not satisfied in this setup. So that's the current situation. There was some recent progress. You can actually prove it. You can actually forbid it in a kind of a variation of this clique, but it gets pretty technical. Okay, so that's all I wanted to speak about.
Questions or comments? Also online, if somebody wants to speak up. If not, let's thank our speaker again.